Our next talk is a, better get it right here. Yeah, it's right there. We're going to hear about cobalt on carbon nanofiber catalysts, and we're very grateful to have Professor Jong.
Thank you very much, Gal. Ladies and gentlemen, it's my pleasure to continue this session on gas to liquids. And in particular, I would like to talk about the effects of cobalt particle sizes. This is a contribution from Linda Bezemer, the PhD student involved in this project, Jos van Dille, associate professor, working with me. I would like to talk about particle size effects in Fischer-Tropsch, and then move on to carbon nanofiber support materials. Then I'm going to talk about the preparation of cobalt supported on those carbon nanofibers, Fischer-Tropsch activity measurements at 1 bar and 35 bar. Just one slide on the background of Fischer-Tropsch. I think we had an excellent introduction to that field. However, just to remind us that we polarize carbon monoxide and hydrogen to higher alkanes and alkenes, indicated schematically by the methylene group here. And we want to reject the oxygen as water in case we start from natural gas as a feedstock. Today I think it is an exciting time in Fischer-Tropsch, you might say third generation Fischer-Tropsch technology, where if you add up the plants that are being either constructed or in an advanced stage of planning, we arrive at 1 million barrels per day of synthetic diesel and kerosene in the year 2009. Just 4 years from now. However, if you take a world-scale plant, typically 100,000 barrels per day, with an investment related to that of multi-billion dollars, from that I calculated the amount of cobalt needed for a single plant. And I did an optimistic calculation, optimistic from the perspective of those who has to buy the cobalt. Then you arrive at 200 metric tons. And why is that such a huge amount of cobalt? And remember the current cobalt prices, etc. You can do the calculus. So with this amount of cobalt, we're not in very good shape, you might say. We will have significant cost for these plants related to the amount of cobalt, and of course even more for the finished catalysts. So cobalt utilization, and thereby cobalt dispersion, becomes a very relevant issue. What Jim was showing us in the previous talk in such an eminent manner, that in the commercial catalyst we typically envisage 5% dispersion. So 95% of all the cobalt is inside the particles and joining the celebration of Fischer-Tropsch, but it doesn't contribute very much. So we would like to improve this dispersion, and therefore I think we must consider particle size effect studies. And so I summarized over the years, and what we see from that is a lot of important contributions of the organizer of this symposium, Carol Bartholomew, and he stated, yes, there are particle size effects, but later on said, look, let's be careful because it can easily be mixed up with support effects. And also Jim was according to that issue. However, we get a kind of somewhat scattered information, you might say, and I would like to point to an important paper mentioned also in the previous talk by Henri Iglesias to Solet on particle size effects. He said no particle size effects. But let's zoom in and realize they're talking about 10 to 200 nanometer particles. That is 0.5 to 10% dispersion. So there is some room for improvement, you might say, but let's zoom into their data. And I picked them from a paper we should all read, working in Fischer-Tropsch 1997 review by Henri Iglesias. And these are the conditions. That they tested all the catalysts and they said, look, the turnover frequency, now based on the total number of cobalt surface atoms, as a function of cobalt particle size, is typically 0.02 per second. Let's remember that figure. 0.02 per second is a typical turnover frequency of commercial conditions per surface atom of cobalt. And it's independent, so no particle size effect. But let's realize again, this is 10 nanometers, this is 200 nanometers, here the dispersion is 0.5%, so my 200 metric tons of cobalt go through the roof, right? We don't want to be there. We should be somewhere over here, so let's zoom into that region. And what we see then, about 10 is minimum, about 20 is the range. Those are the data again from Iglesia. And here are the commercial catalysts, ladies and gentlemen. 20 nanometers, about 5% conversion, dispersion, excuse me. So what is going on here? And that's now the big issue. And I think Jim was referring to that. And we should realize the oxidation problems with cobalt under real Fischer-Tropsch conditions. We make a lot of steam, and already in 1995, workers from Statoil and Trondheim said, look, be careful, you can deactivate the cobalt due to the presence of water, steam, and Bertrand Davis did excellent work and said, look, but this is more specific. He used X-ray absorption spectroscopy and said, the cobalt oxide, the divalent cobalt, will react with the spore, give you cobalt aluminate. Van Steen and Van Loosdrecht most recently also showed that the thermodynamics will shift with smaller particles. Cobalt oxide is getting more stable relative to bulk cobalt oxide. So if you want to make progress in this area, I think we need a support material that is more inert than the conventional oxide supports. And therefore we move to carbon nanofibers as support materials. Well, carbon nanofibers are support materials with these characteristics. They're chemically inert because we have a graphite-like carbon. They're chemically very pure, so activated carbons often contain sulfur when they're from natural origin. If they are from synthetic origin, they contain micropores, which also gives problems in Fischer-Tropsch. So these materials are very pure, but also have good accessibility for the reactants to travel in, for the products to travel out. Specific surface areas high, more than 150 square meters per gram. Mechanically strong, I will show you in a minute. So this is not a fluffy powder some people tend to talk about when you talk nanostructures. No, this is real mechanically strong particles you can handle. And there's a high bulk density possible. This is the poster we will present this afternoon. The high bulk densities above 0.9 milliliters per gram. So what is a carbon nanofiber? This is a high resolution TEM image. The graphite planes run under an angle with the main axis of the fiber. So this is high aspect ratio material. And the interlayer spacing is 3.4 angstroms. So this is graphite-like. And because of the angle of the graphite planes with the main axis, sometimes referred to as fishbone or herringbone type carbon nanofibers. So this is 5 nanometers, so the diameter is something like 30 nanometers in this case. This is the review where we published a lot of this stuff. So moving to lower resolution, using a scanning electron microscope, we see all the fibers quite uniform, but they're strongly interwoven. It's an interwoven structure, and that is key to the mechanical properties. But you see the pores are not micropores, but mesopores, so you can rapidly move in and out of the structure during catalysis. That's very key. But the interwoven structure gives us, on the macroscopic scale, this is 0.5 millimeters, gives us strong, mechanically strong particles that are usable in slurry bed reactors or fixed bed reactors. So this is the type of material we use. There's one big issue if you have this chemically inert material. How are you going to deposit the cobalt? So the next item is the preparation of supported materials using these fibers, but now with the cobalt dispersed on it. And we did a lot of work on it. I just flashed through it because I want to move to Fischer-Tropsch. It just gives you the indication that the preparation is key, because what we need to study particle size effects are narrow particle size distributions. So if you want to compare 3 nanometers with 30 nanometers, you should not have all the sizes in one catalyst. You need 3, 5, etc. And that's a lot of work. So this is one where we used the deposition precipitation method developed by Martin Locke, working at Johnson and Matthey. And it's a very elegant method where we could, in this case, obtain typically 14 nanometer particles And we use 3 independent techniques to study the particle size. It's hydrogen gas absorption, mentioned before, quantitative XPS, and counting the number of a few hundred particles with TEM. So then, this is a representative TEM image. The dark dots are the cobalt particles, these are the fibers. We see uniform distributions, rather narrow particle size distributions. Also can be concluded from the fact that the sizes from several techniques coincide very nicely. This is a high resolution image of that same system, which by the way shows that X-ray diffraction line probably would not give meaningful numbers. So we worked on and on, we used other techniques, we moved to 5 nanometer, 3 to, let's say typically 4 nanometer particles, TEM, low resolution, high resolution, all nice, and then we moved to the smallest particles that we have studied, that's 2.7 nanometer. And then something strange happens, because 2.7 from TEM nicely agrees with XPS, but hydrogen gas absorption is suppressed. So I'll use the quantitative XPS data to pinpoint this particle size. Again, now high resolution, low resolution, we see very nice uniform particle sizes. This table is just to impress you and to say we did a lot of work. So now we move, we do Fischer-Tropsch activity at 1 bar, indicated as low pressure Fischer-Tropsch. Oh, push. Where are we now? This is what I wanted to show. So this is now the low pressure activity, 1 bar. Here are the conditions, low conversion conditions. And this is the, what you might call the cobalt time yield. It is the 10 to the minus 5 mole CO converted per gram of cobalt per second. So per weight of cobalt, so this is for those who have to pay the cobalt bill. And that's a relevant plot. You want to know what can we do to reduce that cobalt bill. Well, here's the commercial catalyst, typically 5% dispersion, so that coincides nicely around an activity around 1. And we move up, when we move to 6 nanometers to 3.5. So that sounds good. The cobalt bill is going down. From the 200 tons, we can already leave a lot in underground. But so we're doing well, moving to 6 nanometers, and we think, well, let's take 4. And then we have a disaster. Then the specific cobalt specific activity goes down. So you might say, what's special about 6? Well, I show you nothing is special about 6, but there's something special below 6. Because until 6, the turnover frequencies are constant. Because this drop is simply a drop due to the lower specific surface area. So let's move to turnover frequencies based on all cobalt surface sites. And we see now that we are at 0.01 per second, so not 0.02 at high pressure, but 0.01 at 1 bar. And we see from 25 to 6, it's constant. So no particle size effects, and 6 nanometers just the optimum because you have the maximum amount of surface size. Okay, but now down we go, and we are close to a factor of 10 lower, so that's significant, that's fun. What is going on there? Well, the first thing I would like to say is, let's first check at high pressures whether this all substantiates, because in industrial conditions, these are typical the conditions. And what we see is very nice, I think. The red dots is from the literature, the blue ones is this work, here are the test conditions, and what we see very well in line with literature, typically 0.02, perhaps 0.03 per second, but then again, down very substantially, the surface specific activity goes down by a factor more than 10. So also the selectivity, I won't talk too much about selectivity today because of only 5 minutes left. And just summarize that the particle size effects are clear. Turnover frequency drops below 6 nanometers at 1 bar, below 8 nanometers at 35 bar. And what's going on? Do we have still the reoxidation of the cobalt, or didn't we succeed to reduce the cobalt? Do we have carbides? Is there such a sensitivity? Well, this is an ongoing study, but I'll show you one piece of crucial information that's coming from Xanes. These are the reduction conditions that we apply, and this is X-ray absorption at the cobalt K edge, and we used metallic foil, that's the black line, and here you see the absorption. Then cobalt oxide, a much more intense white line, and that's due to the anti-bonding states of the cobalt oxygen, and we get more and higher transition probability for the oxidic state. If we now compare our reduced in situ reduced catalysts, we see both for 2.7, the smallest, and 4.7, it's very much metal light. So the bulk reduction is not the problem. That's what we know today. So with that, ladies and gentlemen, I would say these carbon nanofibers are excellent support for fundamental studies. Cobalt particle size, also promoter effects. I can't talk about it today. These are the particle size effects that I would now call clean particle size effects. We have metallic cobalt, and we know the specific surface area very well of these materials. The degree of reduction of cobalt, the bulk reduction I should add, the bulk reduction is similar for all cobalt particle sizes, and the causes of particle size effect therefore are not clear as yet, and that's an ongoing study we are performing. I would like to acknowledge my predecessor, Professor Tropsch, active in transmission electron microscopy, technical staff, Harry Bitter, who's present in the audience, involved in the X-ray absorption studies, Fernando Morales and Bert Beckhuizen work on promoter effects in the Fischer-Tropsch and contribute to the next paper. I thank them for inspiring discussions. The people from Shell for the high pressure experiments, and I thank Shell Global Solution for their funding, and you for your kind attention.
We do have time for a couple of questions, please.
May I ask about the selectivity C5+?
C5+, I'll go back to that. Here we are at C5+ at high pressure. So this is again similar, it's going up, and we touch about 85% C5+, so pentane and higher hydrocarbons.
Hans?
The selectivity, the methane selectivity might be of high interest in terms of chemistry. Methane, yes?
Yes.
It's changing here for the small particles.
Yes. This is at 1 bar. We see basically what, so this is of course a high methane selectivity at 1 bar always. You see this is really going up tremendously.
This could be indicative somehow, no?
Yes, yes, yes. But still puzzling because the hydrogen absorption was suppressed with the highest dispersion. But we can discuss about that.
I wonder if this is support effects. And when you're getting to these small clusters, there can be electronic interactions.
Yeah, but still it's 2.7. It's not that small, of course, for electronic interactions. But agree, we do the X-ray absorption, so yeah.
Yeah.
Could you tell us a bit about how do you get that whole range of dispersions, and also how this support differs with other supports regarding the symptoms?
Yes. So 2 questions. The preparation. That's a half an hour discussion.
Right.
So if you allow me, let's do it in a break. Sintering, we studied the spent catalyst. We did extensive electron microscopy on that to assure that we are not studying sintering effects rather than particle size effects. So you're completely right. This is a very important issue, and we did a lot of work on that. Thank you.
One last question, Neil.
What catalyst do you use to make the nanofibers?
We use a nickel on silica catalyst to grow the carbon nanofibers. We remove the silica afterwards. We remove, of course, the nickel, otherwise we would want lots of methane. That is the key material. But we will show in our poster quite precisely how we do it. So I invite you this afternoon.
Well, thank you very much.